Good afternoon. Can you hear me from the back side? Thank you. Otherwise, there is an option of using headphones if you cannot hear me properly. So good afternoon and welcome to the session for the multicast. We will be talking about multicast in segment routing. What all the different options we have. So this is mostly introduction kind of session where you are going to get to know about different choices which you have. And it is kind of a different tools for multicast. And using these tools based on your need, you can pick and choose any of the choices. So I am Mankamna Mishra. I am from the engineering team. I am technical leader based in San Jose. I code. I write IETF drafts. I work with all of you for the problem statement, come up with new solutions. And the amount of multicast I speak every day, my 3-year-old daughter does introduce me as my dad works for multicast. So some housekeeping that you can join the discussion in the WebEx Teams. And if there are any questions, though I cannot answer right away while talking here, but we can answer it later. We have packed agenda. If you see in the agenda item, each of individual line items are kind of 1 hour discussion by themselves. But we will be just touching the how or what all options you have so that you have a fair idea about what all choices we have with multicast. So segment routing. If we talk about unicast world, in last few years, most of the network are trying to go towards segment routing. And one of the reason going with segment routing is simplicity, which it brings in. There is a simplicity, there is a traffic engineering options, and apart from that, it is trying to remove lots of protocol from the network. And that kinds of really help operational team to be able to debug and maintain the network. What do you want to, what choices we have for multicast? So before we go into the choices, so let's see which all places we have different options where we need to think about how to deploy multicast. So the network, if I look at very high level, we can really segment it into 2 parts. One is your access network and another one is core network. So we are going to go over what do we have for the access side of the network, what do we have for core side of the network. And then we have 2 choices where at some point of time you may be doing layer 2 stretch, and in some of the network you will be doing the IP or L3 VPN kind of network in the core. So how multicast is going to work with segment routing in these 3 different places. Though we already have lots of multicast options today, whether it is ingress replication, PIM, MLDP, RSVP-TE. So if you upgrade your network to segment routing, do you really need to do something for multicast? Is it really needed? So answer is no. Multicast and unicast, both are completely orthogonal. You can still have segment routing in unicast, and multicast, your existing options can still work. But the thought process is, the whole reason you are deploying segment routing or you are going towards segment routing is to bring the simplicity. So can we use some of these principles and do something in multicast as well? Can we do can we bring some simplicity in multicast for our segment routing network? And that is what we are going to talk about. So we will start from the access side or layer 2 stretch. And the first topic we are going to talk about is the EVPN and multicast. So with EVPN, we can have a network where you have layer 2 stretch across L3 core. And for today's discussion, I am mostly touching SR MPLS or MPLS core, but most of these technologies or terminologies are going to be same even for SRv6 or any other network. So using EVPN, we do layer 2 stretch. And in the left-hand side of the network, if you see, we have multi-homing. And multi-homing can be in different mode. It could be all active, single active, port active. There are different modes based on your need. Different modes are provided. We have a concept of DF and non-DF. how exactly my multicast network is going to work in this case. So what happens, we get IGMP report, and IGMP reports needs to be synchronized to both of the peer. The reason why it needs to be synchronized, if you see the concept of DF and non-DF, your either of P or either of peer can be DF. But when you are getting join may come to one of them. It's not necessary that the IGMP join will always land into DFP. So in that case, if we don't have a mechanism to keep both of them in sync, you may never get your multicast traffic. So on the left-hand side, when you do access redundancy, we do support, or we have a defined way of synchronizing your IGMP join between both of the peer. By default, in the EVPN today, we do ingress replication. What it means that when you have multicast traffic coming from the source, it is treated as a bump traffic, and we do IR. When we do ingress replication, it will be delivered to all of the peer. So in this case, your DF and non-DF both are going to receive the multicast traffic. When both of them are receiving the traffic, it is the only DF which is going to forward to your access side of the network. What is the problem with the previous option? It works well when you have only maybe redundancy services for with EVPN. But what about you have a site or you have layer 2 stretch where you have 100 or 200 such places? So if you get a traffic, and if we are doing ingress replication, and maybe you don't need the traffic everywhere. So if you don't need it, you don't want to do 100 copies of the traffic floating around the whole core of the network. It is going to use your bandwidth. So for that, there is something called as selective multicast. So in that case, when you use selective multicast, you exchange your capability to start with. And when you exchange your capability, by default, multicast traffic will not be flooded. By default, multicast traffic will be blocked. It will be provided only if there is a request. So in this picture, if we see all of the Ps around the EVPN network, they are EVPN Ps. You get a join will be synced. Now, when multicast traffic starts flowing, it will be replicated only to those 2 Ps where you have your membership request coming from. So this really helps you to prevent the multicast traffic flood. If you are having some video traffic which is like 4K, 8K traffic, and if you start flooding across the core, it will really take a lot of bandwidth. So this talks about the pure layer 2 and layer 2 stretch. How is this going to work when you go towards L3 VPN? We have a mechanism where we can do redundancy or access redundancy using EVPN, and you can drop it off or hand off the rest of the network with MVPN. So in this picture, if we see, the left-hand side is both of the Ps are part of EVPN. You configure ESI, you configure EVI, and you create a multi-homing all-active segment. If you get any membership join, it will be synced. But the right-hand side of the network, or your actual source, is sitting in the MVPN network. So it is going to use all the MVPN procedures. Today we have multiple profiles. When you go with MVPN, we have around 30 profiles. So these profiles are nothing but different mechanism of underlay and overlay. Some are PIM-based, some are BGP-based, some are with RSVPT, with different traffic engineering options, some are controller-based. So you can use any of those mechanisms in the MVPN network. You can still hand off from EVPN multi-homing, and your traffic will work perfectly fine. So in this case, one of the benefit of this with EVPN multi-homing is your DF and non-DF both will build a tree towards source, and what it will result into that you will be getting kind of live traffic. So when you get live traffic, for any access failure, you will have minimum impact. So in this case, if your top of the P, which is DF right now, fails, immediately NDF is going to pick it over and start sending the traffic towards access. So this gives you the protection of any failure in the access side. So this particular segment covers the layer 2 part of network and the access redundancy, that what all choices we have for the access, what all options we have in the MVPN side. So just to make sure it is understood correctly, that when you say EVPN, where we are doing IR from the head end, you can still do traffic engineering. You can have different policies for unicast, you can have different policies for multicast. Your each multicast traffic, depending on your need and different kind of color affinities which you have configured, you can achieve all the traffic engineering benefit from the unicast for multicast traffic as well. So if we move, before we move to the core part of the network where MVPN is being talked about, if there is any question from the EVPN. Okay, so for the MVPN side, we have multiple choices, but since we are talking about label-based forwarding, which is SRMPLS, RMPLS, we would be talking about MLDP. MLDP as one of the choice. MLDP has been deployed for last maybe 10-15 years. It has been working perfectly fine. MLDP is a protocol which helps you to build point-to-point LSP or multi-point to multi-point LSP. And it is very often preferred for MVPN services. So today, if we see, I think around 60% of deployments for MVPN do use MLDP as option for underlay tree building. And to understand, it is a hop-by-hop protocol where we are doing label exchange and creating multicast tree. So if we see how signaling works for MLDP is, we have these P's and P router in between. We start binding the labels where we say that this is particular FEC. So FEC is nothing but it could be S comma G, it could be S comma G with some verb, or it could be S comma G or some other identifier. So in this case, this FEC, nothing but it identifies the tree ID. If you have some aggregated tunnels, it will identify your tunnel where you might have multiple flows going in. And these exchanges are happening hop by hop, and that's how your replication list will be created. And traffic flows in the reverse direction of your tree creation. Once you have created the tree, how exactly we are going to map our IP flow to these LSPs? So we have two choices. We can do overlay signaling. So when we do overlay signaling, we can use any of the existing overlay. For example, we have been using ROSAN GRE for quite long, where there is a PIM adjacencies between all the edge devices. Or we can use BGP-based next-gen MVPN signaling, where you create a BGP peering between the Ps, and all of the membership requests will be sent over a BGP to ingress P, and that is what going to map your IP multicast with the MPLSP which has been created. That is one choice. The second choice is in-band. In-band is very famous or very useful for the deployment where your scale is very low. Maybe, for example, IPTV. You have 500 traffic, 500 flows. So in that case, you really don't want to go with a heavy multicast MVPN signaling, and you want to let it create 500 states in your MPLS network. So in that case, you can still use in-band, where this FEC is going to carry your S comma G information, and it is going to create a underlay tree using MLDP. Now the question comes, why we are talking about MLDP with segment routing? Because with segment routing, we said that we need to remove some of the protocols which are running in your network during with MPLS. And one of the protocol which we wanted to remove for unicast was LDP. So if we wanted to remove LDP, we are still talking about MLDP. How is it going to work with segment routing network? So yes, it is going to work because you can turn on LDP only for multicast, and your unicast will be still using your SR terminologies. When we say the turn on LDP only for multicast, what exactly it means? So if we really go deep inside, the whole purpose MLDP was using LDP is only to transport this FEC information, or rather I would say that it was overloading the existing TCP connection between the hops to carry this point-to-multipoint LSP information across the network. So when you disable LDP for unicast and let it be on only for multicast, what it does, that it is still using those TCP connections so that we can do FAQ exchange. We can send our MLDP label mapping. But your unicast path is not going to use, or it is not, LDP is not going to do anything with respect to unicast. So, yes. Mm-hmm. So if I understood your question correctly, it is you are using segment routing for unicast, only segment routing. Yes, so if you want to use MLDP, we will have to turn on LDP with this option which I spoke about. This option where you say that LDP is on only for MLDP, the last option, MLDP only. It is a standard defined where once you enable this, your LDP is not going to participate in any of unicast label exchange. So unicast label exchange will be taken care by SR transport. And only for multicast, we will use that LDP transport. So we spoke about MLDP. Now, question comes that how exactly we are going to do traffic engineering? Because the base MLDP is just building the tree based on your IGP reachability or using best path. If you want to do traffic engineering, what all choices we have? So one of the choice is using flex algo. So flex algo provides us a flexibility where you can really segment your network in different virtual network. And these virtual networks can be of different metric. It could be of low latency, it could be low delay, or maybe some of the other traffic engineering metric. And when we use MLDP with flex algo, we leverage all of the benefit what flex algo gives us. It could be your TI-LFA or ODN or any automatic steering. So the way you configure your network is each of the node and link, they will be colored. And based on that, IGP is going to calculate best path only on those particular color-based links. So in this case, if you see, I have two network, which is green and red. Green is being denoted by algo 128, and red is by 129. So now if I really want to see reachability from 0 to 9, 0 and 9 is participating in both of the algo. So in this case, I will have multiple paths, one path from green and another path with red part of the network. So how exactly this is going to work with MLDP? So in case of MLDP, if we are using MLDP for multicast services, we can do support with flex algo. So in that case, your whole network has been configured with green plane and blue plane. And now when your multicast tree building is being processed, so in that case, we define that this particular tree, or you can have a policy which says that flow 1 has to go using green plane, flow n has to go using blue plane. And based on these policies, now we can create our underlay tree in the respective plane. So when you use MLDP with flex algo, you can have same tree. If you want to have a live kind of scenario where same flow needs to go using two different plane, you want to have a disjoint plane, or you want to make sure that your tree is really taking disjoint path. In that case, it can be incorporated with flex algo. And it is when we do use MLDP with flex algo, it is a standard. And the way it has been defined is when we carry the FAQ, at that time we really define which particular algorithm we are going to use for any given tree. So let's see how data plane and control plane signaling works. So in this case, I have two receivers in the right-hand side, have source in the left-hand side. We receive a membership request, and these policies are defined at the head end. where you really map your individual flow to certain color. When membership request comes, we follow our existing MVPN procedures, where you say that I need this particular flow, S, G, from a router 0, which is my next hop, IGP next hop, to reach source. So in this case now, 0 knows that the way I'm going to receive this traffic, or the way underlay tree has to be set up, it is using the 129, algorithm 129. So it is going to allocate a tree, it is going to allocate a information saying that based on the policy, this has been mapped to algo 129. Now, router 9 can do underlay tree building using the existing mechanism, which is MLDP, to make sure that it is going via red links. And once your tree has been set up, you can have your traffic going only through the red plane. Now, if there is any failure, we are going to do all the recovery within red plane. So there is, for the security reason, not just Cisco, across vendors, the way Flex Algo has been defined, we don't leak traffic from one plane to other plane. So if there is any failure happening in the red plane, all the repairs are going to happen within red plane. And this is very useful for some of the use cases where multicast data, for example, financial data. So financial data is really important. So in that case, you cannot lose a single packet, or you don't want to lose any of the traffic for any kind of failure. So in that case, you can have red plane and blue plane of the network, which will make sure that your traffic is always going in two disjoint paths, and the application can decide which of the flow to use at any given point of time. So this talks about the protocol which we are going to use hop by hop signaling. Any question before we go to the next segment of the? Okay. So if we see, the MLDP was nothing but a protocol which was providing you a capability to build multicast tree hop by hop. We have another choice of tree building where you really don't want to turn on any multicast protocol. As there was a question that if I'm using segment routing for unicast, do I really need to turn on LDP also? So yes, we have choice where you can remove even LDP. You have a choice where you don't need any multicast protocol running in your network. But if there is no protocol running in the network, how exactly we are going to program the replication point? Because with multicast traffic, the way it is different than unicast, you have a source and destination in unicast. So it is easy to say that how to go from give a point A to point B. But with multicast, it is going to go to A, B, C, D. How exactly we are going to really insert all these information? So we need some way or some protocol where you can really identify which all nodes are the replication points and go and program it. So we have another way to do it. If you want to remove your multicast protocol, we can remove the multicast protocol and we program these replication points using controller. And that is where treeset comes into the picture. So treeset is SDN or controller-based point-to-multipoint tree creation in the segment routing domain. And what it does is you have a controller. Controller will have a complete view of network, and it can identify that which all nodes are going to act as a replication point at any given point of time. And the beauty of this protocol is now you have removed your multicast protocol completely from the network, and you are only touching those nodes where the replication is going to happen. This does work for SR MPLS, plus work is in progress for SRv6 as well, but for now we will be focusing on MPLS data plane. So one of the important aspect in the treeset is PCE, because when we talk about controller, there has to be some agent which is really going and programming your end-to-end network. So we reuse the SRPCE, which is path computation element, and it is not just used for multicast, it is used for multiple other purposes with respect to unicast as well. So what it is going to do, it is going to collect the information of the whole network. You will have from access to data center, you will get the whole network topology, and based on different intent, it can create a multicast tree and program your replication nodes. So when we go with tree set, there is a replication segment which is defined in IETF. So replication segment is a kind of a identifier, or you can say it's SID, which defines that at any given point of time in any node, which all my outgoing ports are based on some different intent. And it defines a way that your incoming traffic, which all outgoing node it has to go out on. So when we talk about building a tree, or when we talk about multicast, there are multiple things which has to happen in PCE. And the 5 important elements are learning the topology, because now we don't have any hop by hop protocol running which can really go and build the tree hop by hop. So if it is the centralized element which is going to create a tree, it has to learn the whole topology. The second part is learning about root, where my sources are there, and learning the receivers, which all places my receivers are sitting. And after that, based on different intent or different policy, compute the tree. And once tree has been computed, now replication nodes have to be programmed. Before we can program the replication nodes, the identifier, as we said, in the segment routing, the identifier or the tree identifier is your MPLS labels. So we need to know which label to use before we can program the network, and having the mechanism where SRPCE or any controller can program your individual elements. So the first part is learning the topology. So in this case, SRPCE uses BGP-LS as existing protocol, BGP link state. It gets the whole information, our whole IGP database from the network, and now it can run its own SPF. Now it can run different constraint-based SPF depending on the policies which you have configured. And it will have complete network topological view, where it can really identify that how to reach from one node to another node using different constraints. And the second part is how exactly we are going to learn about where the source are sitting, where the receivers are sitting. So we have been using MVPN for ages. We have BGP-based signaling, where BGP does help us to identify the source and receiver. We are reusing that. So in this case, your receivers are still going to use the MVPN constructs, where they identify where the source IP is sitting or where the source P is sitting. It sends the BGP-based MVPN signaling to the root of the network for the given source. And now this particular root is going to request SRPCE or controller that I am the source. I have these 2 receivers who are interested in this particular traffic. Can you please create a tree for me? So now in this case, C and D, sorry, there is a typo, there is no D here, but C and D, they have active receivers. They did send their intent to receive a traffic for a given source. And now A can request it to SRPCE to calculate the tree based on different policies which has been configured. So SRPCE in this case gets the request based on different policies what you have configured for this particular flow. It can compute the whole tree, that which all nodes needs to be programmed as a replication point. The important aspect comes is the label allocation, that which label we are going to use. Because till now, if you look at the MPLS paradigm, label was a local policy. I mean to say, each individual boxes, they had their own local labels. So when you run your end-to-end unicast as well, unicast label may be accidentally, it may be same across two boxes, but truly speaking, hop by hop, you had label allocation and we were mapping that incoming label is this, what is going to be outgoing label. But in this case, can we do something similar? So answer is yes. You can have a localized label where individual replication points are having their own local label, or you can have a global label. So the benefit which global label gives, when you are debugging, you really don't need to go and track individual label mapping, that what was the incoming label and what was supposed to be outgoing label. So in this case, we can have a global label allocation from the predefined range of the label, which is pre-configured. And this label will be allocated for a tree. Now the scope of label is going to be your flow plus root. So local label will be assigned, and this label is global label will be assigned, and this label is going to be used across the whole network for a given tree. So this label basically provides you the information about the whole tree. And after that, once we have calculated the tree, we can use existing PSAP algorithm to program the replication points in the network. So it is not just the PSAP, we can use netconf, we can use REST APIs. We have multiple ways where srpc can talk to any of the nodes. So once you have programmed the replication points, now, so in this picture, if we see, we have a policy which says that from root is A, and leaf are C and E, and the label which is allocated for this particular flow is 15,000, and that is programmed in the network. When you have your flows starting from source, it will be coming with label 15,000. Now when you really want to debug this particular flow, whether which part of network this flow is going, if there is any issue, you can use just the 15,000 label to identify this particular flow. So we have, so this talks about the mechanism how tree is being building, but depending on use case, we have two choices, that how exactly we are going to build our tree. And the two choices are static point-to multi-point policies. Second one is dynamic point-to multi-point policies. Where do we use static policies? So there may be a use case where you already know that these are the nodes where my sources are connected, and these are the set of receiver nodes where always my traffic is going to go. You don't want any BGP-based signaling. You don't really want to keep provisioning the trees on the fly. So for those kind of use cases, we can have a static tree created well in advance, and it is kind of tree is always sitting in the network. Whenever there is a source or whenever there is a new source coming, traffic will flow. If source is not there, traffic won't flow, but tree will not go away. The dynamic policy is similar to MVPN, where dynamically your receivers are sending join, and dynamically you are creating the whole tree. When receivers are gone, your tree is also being torn off. So static policies, we can provide or we can configure from the router itself that these are my root nodes, these are the set of receiver nodes, and it will be provisioned at the start of the network itself. Whenever you configure, your policies will be installed. In case of dynamic policies, it is something similar what we do with MVPN, where you have the srpc, which is talking to your whole network, and you define a policies. Based on policy, you provide a information that where all your source is sitting, where all receivers are sitting, based on our MVPN signaling. And after that, we calculate a tree. This tree will exist till the time these joins are there. So as soon as join go away, this tree will also go away. What are the different use cases which we can do with tree set? So with tree set, we can do disjoint tree. So in this case, the sample policies which you can say is from the PCE that I want to create a tree which is going to start from PE1, and my leaf nodes are R1, R2, R3, and I want to exclude green and red link. Using this particular affinity, now your tree can be built from P1 to rest of the receive R1, R2, and R3. In similar way, you can have a different tree or second tree created for same flow with different affinity. So what flexibility this provides, that you can have a disjoint tree created on the fly from SRPCE. The second use case is minimum latency trees. So instead of giving your link color, you can say that I really want to create a low latency tree. So in this case, we are going to use performance measurement. So when we start building a tree, we will see that from PE1 to these receivers, which is the low latency link available. And based on that, we are going to create the trees. And if there is any change, to handle that, PM is going to really notify us that there is a change. Now there is a new delay got added. So based on the delay, tree will be recomputed and it will be reprogrammed. And to make sure that you don't have traffic loss, because when controller is programming the tree, you don't want reprogramming to be causing any traffic loss. So in that case, there will be a make before break, where your tree is going to be made in advance before your flows are mapping into the second tree. And by the way, when all the topics which we are talking here, they are available in different releases, different product lines. So please don't quote me for any existing product line and release. So that is different discussion. The important aspect, or something new which is coming now, is visualization and provisioning of the tree. At the start of presentation, we said that the whole reason why you are going towards segment routing is the simplicity and your maybe better debuggability and overall operational experience. To have that, now we have a way where we can really visualize your whole multicast tree, and this is available for TreeSid as of now. And you can visualize the whole tree, that how your tree has been built. You can visualize different aspects of the tree. What are the policies, whether it is a static tree, it is dynamic tree, what all are the names of the policies. So everything, it can be in your dashboard, which is a crosswork dashboard. Using that, you can visualize your whole end-to-end tree. There are these are the different aspects where you can really go inside individual tree. You can see that which all path it is going through and what all different policies you have configured, and whether it is a static tree, or if it is a static tree, what all are the nodes, what are the role of these nodes. Are they source node, or transit node, or maybe the tail node? So it is going to provide all those information. If it is a dynamic tree set, so it is going to provide information about the dynamic policies, what labels have been allocated for a given tree, and all the parameters of a given tree. And it is still work in progress. More and more things are getting added with the new release which is coming in April. So to summarize, when we say that we want to really simplify our multicast delivery, we have a few choices. So if you want to do non-traffic engineering multicast in segment routing network, MLDP is choice for SR and SR-MPLS network. SRv6 right now work in progress, because there is a lot of discussion going on even in the ITF about what will be the best way to carry multicast traffic in SRv6 networks. Though Ingress replication is one of the choice which is being discussed. And if you want controlled path, which is traffic engineering path, so we have a two-way. How you want to compute your tree. Do you want it to be distributed manner, or you want it to be in centralized manner? So for distributed way, we have MLDP with FlexAlgo. And for the centralized way, we have TreeSid with PCE controller. Everything which we spoke about, none of this is really proprietary solution. All of them are standard. Some of them are already RFC. Some of them are still going through the process of IETF because it takes few months of or few years of effort to really go as a RFC. And we have some more documents, or we have some more links here. If you really want to know about what is happening right now, what all new things we are doing, you can look at either of these sites, and this will give you all the information. So thank you. And any question?